Hello everyone. Welcome to the another one-shot review of AP Calculus ABBC. We are in Unit 8. This is application of integration, and in this video I will be giving you the fundamental concepts of calculus, particularly integral calculus, and how it is applied in solving real-world problems, including finding areas to volumes. And this is the most important thing. And also we have the distance traveled, the accumulated functions, and the arc length, those also covered. So let's dive into this and let's learn the practical power of integration. So first, finding the average value of a function on an interval. Average, we know, right? Sum of the values divided by the number of values. So it's very similar to that, but how we are going to apply integration on this? Let's see. So the average value of a function f of x on the closed interval a comma b is given by 1 by b minus a to b f of x dx. And this is nothing but mean height of the curve, right? So there is a curve, its height is differing throughout, but if there is a mean height, so like if you're flattening this, what will be the height? If you suppress this, what will be the height? We are trying to find that. And this formula we can use for any function, right? So one quick example, write the formula, and the function is sin x and the interval is 0 to pi. So plug in, this is pi, this is 0, 0, pi, and sin x. That's it. So plugging in, and we know the basic integration. This integration is quite simple. So sin x, it's minus cos x. Then apply the limits, upper limit minus lower limit, and evaluate it. That's simple. So this is the average value of this function at this interval. And when you're changing the interval, the height, the average will also change. Right? This is how it is. And what we are doing, we are finding many heights, right? By making number of rectangles, which means it connected with integration. And sorry. So we are finding the mean height, and this dotted line is the mean height, which is 2 by pi. That's simple. The average value is. Okay. Now, connecting position, velocity, and acceleration of function using integrals. So these things we have already learned in differentiation, right? Now using integrals also we can connect. So if s of t is given, then you can differentiate. S dash is velocity, s double dash is acceleration. But what if they give acceleration and you are in need of velocity and a of t, s of t? So we have to go back. We have to undo the differentiation, right? From acceleration, if you undo the rate of change, you will get velocity. So going back is integral, and it's quite very simple. S of t, when you derivated velocity, double derivated acceleration, or you can derivate the velocity. If you have acceleration and you need velocity integrated, and most important, yes, I will get velocity plus constant is important, right? And if you integrate the v of t, you will get s of t. And yes, again, an integration constant is important. Now, a quick example. An object is moving along a straight line and its acceleration is given by a of t is there and t is in seconds, and t is 0, velocity is this, and position is this. When time is 0, find the velocity, find position, determine when the object is rest, find the total distance traveled by the object. So velocity you need. From acceleration, you know how to find velocity, integrated. Position, integrate your velocity function. And when it is rest, when velocity is 0, the object is rest. And total distance, we have to use s of t. Right. Now, let's do one by one. Find velocity, a of t to v of t is just integrate a of t. And my a of t is 4t minus 2. Integrated, just apply the power rule and make sure you are giving this constant. Okay. Right. So this is important. And next step, this is not unique answer, right? So we need to find C. For that, they have given a clue. When time is 0, velocity is 3. This is given to us, right? So you just plug in velocity is 3 equal to t, right? You can just plug in to find the C. So C is 3 and you just replace the C with 3. This is your V of t, right? We got V of t. And next, find the position V of t to S of t because we have V of t, right? So again, integrate the V of t. And that's simple. Just write the integration and start integrating basic power rule and S plus constant. We need to find the constant again. For that, they have given a clue. Our time is 0. The position is 5 meter. The same thing, we are plugging in 0 for t and equating S of 0 is 5. We got C is 5. And this completes S of t. That's simple. Okay. Now C part. Determine when the object is at rest. The object will be at rest when V of t is 0. We already know V of t and equate to 0. And this case, you will be trying factorizing, but you won't get any answer. So you check the discriminant, b square minus 4ac. This is b, this is a, this is c. And this is less than 0, no real root. So the object is not at all rest. It never comes to rest. Got it? And find the total distance traveled on this particular interval. So total distance is 0 to 4 modulus of v of t. The rate of change of the position. It's not about S of t. The rate of change of S of t means v of t. And total distances, it's again a positive one, right? So the modulus doesn't affect. So you just integrate using power rule, plug in the values, and you got 1165 meters. Right? That's simple. 8.2 is. Now 8.3. Using accumulation functions and definite integral in applied context. Accumulation function, there will be a rate of change function will be there and the area under the curve. We will be accumulating that. So we have many real life situations where we will use definite integrals. So the integral will help us to find total amounts, like from the beginning till this, how much added all together. So distance, area, volume, distance we just now did, right? And total distance traveled when velocity is known. You can't use S of t. Total area under a curve and total work done by a force. When force is given, you can find the work done, total charge accumulated over time, volume. So we will learn about volume in much broader way. So these are some practical applications. Now, let's recall what is accumulation function. Accumulation function describes how a quantity accumulates over time. So from like your watering droplets had been collected from time 0 to 1 hour, the jar will be filled. So at like 1 hour, 60th minute, there will be 10 drops. It doesn't mean the volume is 10 drops. Altogether, you need to accumulate. So it depends upon the rate of change. It depends on the rate function. So A to B from what to what, like the timing and the bounds, then rate function, and we need to integrate that. This is the accumulation function. And so very simple in solving. Identify rate function for your context. Set up the definite integral. Here we need to be very careful with the function and the interval, the bounds. Evaluate the integral. We have learned a lot of techniques and interpret the result. Since it's a practical problem, the way we interpret it, it's not just the volume is this, right? So we have to interpret the result. And we have a simple example. Suppose a force is applied to move an object. Find the total work done from t is 0 to t equal to 3. This is a rate function. If you integrate this, you can find force. Sorry, you can find the work done. So it's very simple. Integral 0 to 3, 5t square dt. And simple integration. And plugging in the values, you got 45. So the total work done is 45 joules. Right? Now, 8.4, finding the area between curves expressed as function of x. So in area between curves, we have many subdivision. First one is expressed as function of x, like y equal to sine x. Like x is a independent variable, y is dependent. Let's see. So given two functions over an interval, the area between the curves is the integral of the difference between the functions over that interval. Very simple. F of x minus g of x dx. But which function should I write first? If you write f of x at first, it means that is the higher curve, right? So if this is one function, is f of x, and okay, this is so LO is f of x, this is g of x. So from this interval to this interval, f of x is bigger, so that will hold f of x minus g of x. G of x is lower, higher curve, lower curve. Then from this interval to this interval, red is higher curve, yellow is lower curve. So in that case, I will change it to a to, okay, c to d something, and g of x minus f of x dx. Right? This is very important. What if you do like wrongly? Instead, a lower curve minus higher curve, if you do, you will get a negative answer. That's it. Area cannot be negative. So in that case, okay, you can just correct your errors. Right? And so how to solve this? Identify the functions, which is first, and for each interval it might. So a rough sketch is will be a good one, right? And ensure that f of x is the curve above and g of x is below. If you write f minus g. Find the point of intersection. Here the bounds will be, so what I did, the point of intersection of the two curves, right? So that is very simple. Just equate them and solve for x. And this will give the limits, or we can say the bounds of integration. Now set up the integral and make sure the difference is always positive. Evaluate the integral and solve it to find the area, then interpret the result. That's very simple. A quick example, find the area between the curves f of x is x square and g of x is 2x. Okay, what is the first thing? Which will come up? F of x is x square and 2x. Okay, actually it will pass to like this. So we need to find this area, right? And the point of intersection will be here. Wait. This point to this point. So throughout the line is bigger, g of x is bigger, f of x is lower. So write and find the point of intersection. You just equate the function, you solve for x, x is 0 to 2. Now, set up the integral x square minus 2x. So I'm just plugging in. What happened here? I got a negative answer. Why? Because 2x is the bigger upper curve and x square is the lower curve, but I did x square minus, I did lower minus upper. So that's why I got a negative. So this is wrong. And we can go with the correct form. 0 to 2, 2x minus x squared, and you will get a positive answer. Square units. That's simple. Okay. I can show you this example over here. Area between the curves. Right. Okay, let's move. Now find the area between the curves expressed as functions of y. What if x is x is dependent, x is equal to y square. So the parabola will be something like this, right? And x is equal to y. It will be something like this. And again, same concept. Only we need to sketch the same, and the intervals will not be the x values. The intervals will be y values. Okay. That's the only thing we have to take care, and rest everything is very similar to that. So we are calculating area between curves over an interval for y values rather than x. Okay. So if y is your independent, then limits of integration is y. Identify the curves. So these functions represent horizontal portion of the curve. Determine the limits of integration. Again, simple. It's equate them. Solve for y. Now, set up the integral. So when you memorize, use c to d so that we won't confuse with. Then only we will get, okay, we need to plug in y values instead x. And f of y minus g of y. Here, f of y is the rightmost curve and g of y is the leftmost, because horizontally when you see how we are finding the integral means, we are making the rectangles horizontally. It's not like this interval, right? So we are making horizontal. So here we will check which is the leftmost, which is the rightmost. Okay. So rightmost comes first, leftmost comes next. And evaluate the integral. That's simple. Find the area between the curve x is y square and x is 2y. So x is y square. It will be rightward parabola like this. And x is equal to 2y. It will be something like this. So we need to find this area between the intersection. Maybe they can meet here. Okay. And we need to find this area. So first, x is y square, x is 2y, point of intersection. We got 0 and 2 in form of y, not x. Okay. Now, set up the integral 0 to 2 y square minus 2y. The rightmost is, I use y square. Just a second. But I got a negative. The problem is, this is my y, x is equal to y square. This is my 2x. Who's the rightmost? The line got extended. That is the rightmost, right? So it will be 2y minus y square, right? And applying it correctly, I will get a positive answer, 4 by 3 square roots. That's simple. Now, moving on to 8.6, find the area between curves that intersect at more than 2 points. This example I have already given you. So, when the curve intersect multiple times, this is a curve, and one more curve is like this. This area you need to find, right? So, each interval I need to work. From this to this, A to B, red is above, green is below. And when I switch, green is above, red is below. So each interval I have to work by checking the upper and lower curve, right? So find the point of intersection, determine the intervals. It's not always single interval. It can be like, as I have given you A, B, C, multiple intervals. Break them into subintervals, set up integral for each subinterval. One by one, you need to solve and add up all the areas. It's always upper minus lower curve dx. Dx means I'm slicing the curve in this way, vertical rectangles, like along x. And dy means I'm slicing the curve with horizontal rectangles, which is along y. Got it? So here is an example. So intersection is this to this, and then this to this. I will solve. For this, this will be the upper curve. This is lower. For this, this is upper, this is lower. So we have to change the integrand in such a way. Find the area between the curves f of x is x cubed minus 3x and g of x is x over the interval where the curves intersect. So that's what I have given. Points of intersection, equate them and solve for x. I got 3 points. So minus 2 to 0, 0 and 2. Let's set up integral. First, minus 2 to 0. Okay. So for minus 2 to 0, the curve, cubic curve is up and the line is below. So minus 2 to 0, x cube minus 3x minus, this is f of x minus g of x category. And rest you can evaluate, use the power rule and simplify. You got 4 square units. Next, second area, 0 to 2. Line will be the upper one. This will be the lower one. So, right, this time I got a negative. You know what? Because it's x minus, like g of x minus f of x is the correct one. But I applied the reverse. So I got a negative. But still you can change that. And let me show the correct one. So if you do this correctly, you will get positive 4 square units. So total area is 8 square units. That simple it is now. Right. Volumes. So we have covered areas till now, right? So there will be a curve. Your aim is 2 curves. Your aim is to find the point of intersection. And if your slicing is with respect to, like, if your area is with respect to dx, then you need to find the limits along x, right? And it's always upper minus lower. And if you are doing with dy, so you will be making horizontal stuff, and your limits will be y values. These are the simple changes, and here it's rightmost minus leftmost. Got it? This is all about area. Now into the volumes. Volume with cross section, squares and rectangles. So what is basically volume? If I have a cylinder, I'm telling it's pi r square h. The base is circle, pi r square. It depends upon height. So if you keep the pi r square on and on and on till the height, it's the volume. So if you slice them like you will get a flat 2D shapes and all the areas accumulated together to give volume. So volume is accumulated area, like A to B, area function. If you accumulate, you will get volume. That's simple. Now the cross sections for this, its circle is the best one, but we will be dealing with some random curves, right? So first is square and rectangles, then we have triangles, semicircles, so we have lot many. Let's see how to do that. First, understand the cross section. Cross section of a solid shapes like squares. So if I have a curve like this and I will rotate it to form a solid. Okay. So in that cross section, I'm going to make squares or rectangles. My cross sections will be squares or rectangles, and I need to find the volume. And here also x or y axis, both the revolution can be done. So for volume is very simple. It's accumulation function over area. And bounds also it's important. Let's see how to do that. First, find the cross section. If it's a square, if it's given square, area function is side length the whole square. And cross section, if it's a rectangle, base into height. Right? The base will be usually from functions and height may be constant. Height will be changing. Right? Sorry. Now. Okay. So here find the volume of a solid whose base is bounded by y equals square root x, y equals 0, and x is 4, with cross sections perpendicular to x-axis being squares. So squares means side length. What is the side length? So y is equal to root x is something like this. Y equal to 0 is x-axis. Okay. Then x is equal to 4. It's somewhere over here. This is your base. Okay, let me shade it. This is your base and you're gonna rotate it along x-axis. If you rotate this slice, you will get so it will be here, 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 here. In such a way, it will form a nice kind of a bowl thing. Okay, so that is the volume had been made. So we need to find the side length because you're going to take the cross section as squares, right? So the base will be y is 0 and square root of x. So it's just a vertical distance and it won't be a number like side length is not 5 centimeters, something like that. It will be a function. So here we have vertical distance from y is equal to 0 to the root x. So this is 0 and it will be varying, right? If you find the vertical distance, right, it will be varying. And so what is the vertical distance from this to this? Root x. They will be maintaining. So root x is your side length and area will be root x the whole square, which is x, right? That's it. And you just integrate it using power rule and plug in the values. You got 8 cubic units. That's simple. Now, find the volume of solid whose base is region between y equal x square and y equal 4, with the cross sections perpendicular to y-axis being rectangles. The height of each rectangle is twice its base. Okay, so here the region is y is x square and y is 4. Cross sections had been taken along y-axis and its rectangle. Okay, first understand base of the solid. The base is bounded by y equal to x square and this is how it is. and y equal to 4, something like this. So this is your base. And you're going to rotate it over y-axis. So you will be rotating throughout and come back to the same position. This is the base of the solid. So y is equal to x squared. We are just making with respect to y-axis, right? So x plus x is a function of y, then x is equal to plus or minus root y, right? And dimensions of the rectangle. The base of each rectangle is horizontal distance from x is 0, from x-axis to the curve, right? And x is equal to root x. This is the root y, right? So this is the distance. And now the height of each rectangle is twice the base. So base is the horizontal distance from x is equal to 0 to the curve part. And height is 2 times of root y, right? So horizontal distance is what? Just subtract them using modulus and you will get root y again. Okay. Now, area of cross section is base into height. We got base is root y. This is 2 root y, 2y. And volume of the solid is this 0 to 4 a of y dy. And this, okay, bounds. The bounds is from 0 till 4. Only we are working, right? So 0 to 4. And we have plugged in and we have simplified the volume of the solid is. And it's again simple. I'm not repeating it because it's very simple to you. So the volume of the solid is 16 cubic units. Now, volume with cross sections, triangles, and semicircle. Okay, let me show you how using triangles we can do the volume stuff. So this is the simple example I can give you. Let me share the screen. Here you can see. So triangular cross-section type, you can make it an isosceles or isosceles right, equilateral, right, in such a way. So I'm making an equilateral triangle. This may curve f of x is x, and your bounds you can set from 1 to 5. Number of cross sections is 50. You can make 100 even. Let's see. Here is a 3D animation for you. Okay. Okay. Right. So let me animate it. You can see. You can watch how it is being done. So the triangle is we are just making throughout, and it forms a volume, right? And here you notice. Don't look the 3D now. Here the wait. So look at this. The base is being the same, right? And the base is growing. The triangle part is also going since I make the equilateral stuff. So it depends upon. So if I change into isosceles, it will be an isosceles. And let me animate it for you. This is how we are calculating the area, volume. Okay. So accumulated area of triangles. So we have to, we should be thorough with the basics of triangle. Okay, now into the problem. Let's see one basic problem and let's see the idea behind it. Again, each cross section is function of the version typically. So we need to express that skill is much needed here. So we know area. If it's a triangle, find triangle. But if they mention isosceles, so make sure I used a particular formula. And sometimes you have to express as x form or sometimes y form. That's the thing we have to take care of. So this is general formula. And cross sections, if it's a triangle, isosceles, half base square, just to square the base. Other triangles, half base height. If it's a semicircle, pi by 2 diameter by 2 the whole square, and it's pi by 2 diameter square. Right, these formulas. So you will be looking for height and base and diameter in these cases. Right. Find the volume of solid whose base is bounded by y is x square. It's very similar to what we did before, but this time your cross sections will be isosceles right triangle, where the legs of the triangles lies along the base. Okay, base of solid is formed by y is x square and y is 4. Quick sketch on it. So this is what, and we are going to make triangular stuff, and we are going to make it along y-axis, right? So this is your triangle. Then when it comes here, this is your triangle, so such a way. Now dimensions of, it's not rectangle, sorry, it's a triangle. Okay, so base is what we need. For isosceles, it's just base square. What is the base? It's the distance between the curves. So what is the distance between the curve? Y is equal to x square, and x is equal to, since we are doing this in form of cross sections along y-axis, so we have to frame like this: x is equal to plus or minus root 5, and the distance will be 2 root 5. So from this to this and this to this, 2 root 5. And area also we can define it here, half 2 root 5 the whole square, 4 by 2, which is 2 root 5 square is y. Now area of cross section is y. Now set up the integral and solve for it. Plug in those values. You got 16 cubic units. That simple it is. Okay. Now find the volume of solid whose base is region between y is root x and y is 0, x is 4, with cross sections perpendicular to x-axis being semicircles. Okay. Base of solid, y is root x and y is 0 and x is equal to 4. Okay, this is root x, this y is 0 and x is 4. So this is your base. And we are going to make the cross sections being a semicircle, kind of semicircle like this, right? Starting from here, 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 like this. Now, diameter. We need diameter for this. Diameter of the semicircular cross section is the vertical distance from y equal to 0 to y equal to root x, so which is d equal to root x. Vertical distance are very simple. Just plug in those values, f of x minus g of x or k. Okay. Right, so it will be pi by 8 diameter square. Pi by 8, my diameter is root x square is x, so it's pi by 8x. And set up the integral. This is area of cross section. We are doing from 0 to 4, and it will be x, not y. Right? And just integrate it using simpler rule and plug in those values. The volume of solid is pi cubic units. That's simple. Now we have some other methods. Volume with disk method, revolving around x or y axis. In both the axes we will learn. So what is disk method? Disk is something which look like this. Right? It's not a oval, but it's kind of a disc shape. It can be a circle, something like this. Right? So it's a flat, curve, round shape. Not exact round, but it can be oval, circle, anything. Now, the disk method is to find volume of a revolution when a region is revolved around an axis. This method will slice the solid into thin circular discs. So, for example, circle I said no. So here you will slice it into thin circles and you will find the area. The accumulated area is area function, and if you integrate, you will get volume. The same concept. Okay, and this is how. Okay, let me show this with the animation. Disk method. Okay, here we go. Okay, hope you can see it. So here you have to give your function. For example, like f of x is x, if I'm giving, and you want to rotate about x-axis and x-axis or rotate about y-axis. Here we are rotating about x is 0 and lower bound is 0 to 2. Volume is evaluated here, but how we did it? Let me play this. Okay. Here you can see the animation. So this is a kind of a cone shape is formed, right? So we are making most finest angles and we are making a lot of slices. This is called disk method. Okay. Right? This is the disk. had been doing. Okay, so finite disk. And let me make it for sin x. This is how the area, the volume calculation will work under disk method. Now, right, I hope this might give you an idea. Now we are moving to the lesson back. Right? So if a region is revolved around the x-axis, it's pi a to b r of x the whole square dx. If it's around y-axis, c to d r of y. It should be a function of y, and r means here I'm mentioning it's a region around x-axis, region around y-axis. And r of x is radius of the disk. So the radius will be changing, right? So if you something having like this, first radius will be this big. And when you're moving it, it might go smaller. So it's a radius of the disk, uh, that is distance from axis of revolution. When I'm rotating in such a way, then it's x-axis revolution to the curve. And AB or CD, AB for x and CD for y. Now cross-section of a solid is a circle with radius. And area of each disk is pi r of x the whole square or pi r of y the whole square. We need to calculate r of x and r of y. First example. Find the volume of solid obtained by revolving the region bounded by y equal x squared, x is equal to 2 around the y-axis. Y equal to x square, x is 2, and x-axis, right? So volume of the solid obtained by revolving around. So you will be around, revolving it around x-axis, like this, right? And let's start. Visualize the problem. The curve y equal to x square form the boundary of the region, this. And the radius of the disk at any point is given by the curve x square, right? And we are starting from like x-axis only. So it will be, set up the integral for this, r of x is x square. And the formula is r of x the whole square, like pi r square, right? So in such way, x square the whole square, this is important. And it's from 0 to 2, we know that very well. Let me show. From here to here, we are evaluating it. So compute the integral, its power rule, and plug in those values. The required volume is 32 by pi by 5. Okay, so once you've got the respective region, then setting up the integral and the limits, it's over. Like we can easily solve the rest. Right, and next quick example. Find the volume of the solid obtained by revolving the region bounded by x is root y is 0. It's all in terms of y, and we are rotating, we are revoluting with respect to y-axis. So visualize, x is equal to root y decides the region boundary. Now the radius of is r of y, which is x is equal to root y. And from y equal to 0, right? So it will be root y minus 0. That's it. So r of y is root y. And when you square it, it's just y. And apply the limits. Okay, for the limits, it's 0 to 4. You can directly give. And sometimes we need to find the limits by us using the point of intersection method. Right. Now, the simpler one. And it's just differentiation again, integration. And compute the integral, evaluate at the points, and you got 8 pi. The volume is 8 pi cubic units. Now, the disk method. For other axis, so we did x-axis, y-axis. What if x is 4 or y is -5, something like this? Yes, still the volume will work, but slight changes. When a region is revolved along an axis that is not the principal axis, x or y, or like this form, another vertical lines. The radius of the disk only we have to adjust it, right? And it's very simple. The distance between region and the axis of revolution. So far you did root y minus 0. This time you will do root y minus 4. That's it. Okay, if it's your axis is x is 4, if your axis is x is 4. Okay. That's simple. Adjusting radius is the only thing. Now, same formula, and we need to adjust the radius. How will you adjust the radius? If the curve is above x-axis, above the axis, r of x will be modulus f of x minus k. Below means the axis will come first, then the curve. Okay, for horizontal. For vertical axis, f of y minus k. If it's right, curve first. If it's left, curve at second. That's simple. Now find the volume of the solid obtained by revolving a region bounded by this from x is 1, y equals 0 around the line y is 2. Okay, so it's a horizontal stuff. Now, visualize the problem. Y is equal to x square and the line y equal to 2. This is the basic things that define the region. The radius of the disk is vertical distance from this to this. So you got, okay, and one more thing is x square and y equal to 2. So above 1 will come first, right? So 2 minus x square. That's it. You got r of x. Now you just set up integral. Okay, and here we go. So this is the formula and plug in those values. 0 to 1, 2 minus x square, the whole square. This whole square is from the formula. And compute it and evaluate it. Basic power rule. You got 43 pi by 15 cubic units. That's simple. Now, quickly the next example. Find the volume of the solid obtained by revolving the region bounded by this around the line. So it's a vertical revolution now. Very similar. Only thing you have to concentrate is adjusting radius. That's the one extra stuff we have here. So the base is root x and the line x is minus 1. Define the region. Radius of the disk is horizontal distance between these two. And this is x is minus 1. And this is root x. Right? So you will have something like this. Oh, you need to convert this into y form because around the line, so it's about y axis. So see, you can't make any region over here. So y equal to x means x is y square. So rewrite in terms of y, right? And we did that, and then you plug in. So now it will make sense. Okay, if x is y square, it will be something like this. Right? So y square will be the rightmost minus the leftmost curve, and y square plus 1. You got you got your r of y. Now set up the integral using the formula, and the y values should be plugged in. Okay, so 0, y is 0, then x is 4. So when x is 4, y is 2. Make sure you're calculating that also. That's it, and plug in and compute the integral, evaluate it, you will get this 206 pi by 50, right? Now 8.11, there is a new method called washer method. Washer will something look like this. It's look like a disc, but it will have a hollow stuff. Okay, maybe, wait a minute. It will be hollow here, and this is the disc. Same thing. It's a kind of a circle, but it have hollow stuff inside. And volume of this washer method is r outer x minus r inner x because we have two circles, right? So we are doing that. For revolution of x-axis, it's based on x. For revolution of y-axis, y, it's r outer minus r inner. How to find r outer? Distance from axis of revolution to outer curve. This is your axis means this to this outer curve, this to this inner curve. That distance is r of outer and r of inner. Okay, now find the volume of solid by revolving the region bounded by y equal x square and y equal root x around x-axis. Right? So here, using washer method, the curve y equal to x square and the line y equal to root x. Y equal to root x. Right? So this is the region we need to, once you revolute this, okay, this kind of stuff along the x-axis. Now, The radius of the washers are r outer x, which is root x, and r inner x, which is x square. So from your axis to outer curve is root x, inner curve is this. So here we will use washer method, right? When two curves, when there is a hollow stuff. And set up the integral, outer minus inner, then. For those two curves, if you find point of intersection, those are the bounds. And plug in, compute the integral. It's very simple, power rule. So all the examples I have taken is power rule stuff. So that's why. 3 pi by 10, and I'm not explaining this much, and that's very simple even to you, right? And we got a required volume. Now, what if it's around y-axis? They itself give in form of x is equal to stuffs of y. So first visualize x is y square and 2 plus y square, define the region. Radius of the washes or outer. So just a rough sketch. X is y square. Okay. So here we go. R outer y is 2 plus y square. R inner y is y square. And set up the integral. Bounds are given to us sometimes. Oh, I didn't show you, right? Okay, so the bounds you can just evaluate here. It's not given. Maybe it's an error. So just intersection you can do. And it should be with respect to y. That's it. So solve for y. 2 plus y square. And this. So it's 0 to 2. 2 plus y square the whole square minus y square dy. Now compute the integral, and it's a basic power rule. You'll get 56 pi by 3 cubic units. Right. Now, volume with washer method revolving around other axis. Yeah, inner outer stuff whenever it's washer method. And it's exactly a similar one, right? Other than like y equal to k, x is equal to k, there's no difference. But yes, adjusting the radii will differ. It's same like what we did in disk method for other axis. F of x minus k, outer one, curve first, then the axis of revolution. Inner curve, g of x minus k. This is for y equal to k. And this is for r outer and r inner. Right? So here we go. Now find the volume of the solid obtained by revolving the region bounded by y equal x square, y is 0, x is 1. Around the line, y is 3. Okay. So the defined region is by y equal x square and y equal to 0. Axis of revolution is at y is 3. Radius of washes or outer 3 minus 0, just 3. Inner 3 minus x square. Set up the integral, and bounds also we need to find. And it's from 0 to 1. Okay, so it's around the line y equal 3. So 0 to 1, and plug in those values, compute it. It's very simple, and you will get 9 pi by 5. Again, a similar kind of problem. This time around the line x is minus 2, washer method. So the curve is this, axis of revolution. Find radius outer, radius inner in terms of y, because it's a vertical revolution, right? The axis of revolution is vertical stuff. Set up the integral, find the bounds, compute the integral. That's it. You will get it. Now, the key differences between disk and washer. If you see a hollow region, that is no solid object, washer will have a hollow inside. Cross section, this is solid disk here, kind of a disk with a hole. Here only single radius, here too, and this is the formula difference over here. Now 8.13, So volume we did, it's basically, let me recall it quick. It's basically accumulation of area functions. And we have different methods, right? So the traditional method, disk method, and washer method. So main thing, we have to define the region, work on the bounds, right? Now, arc length of a smooth planar curve and distance travel. These things also can be found by integration techniques. So let's get into it. What is arc length? If it's a circle, if you want to find from this point to this point, this is the arc length. Not only for circle, this is an arc length for the sine curve, right? So the formula involves integrating the length of infinitesimally small segments along the curve. Along the curve, very, very small segments we will be considering and we are adding it up. Very small, not even like this, kind of a dot, kind of infinitely small. So the curve should be like this. Their derivatives should exist and they should be continuous. I'm telling derivatives here, right? So arc length formula for a curve from x is equal to a to b is L is a to b square root of 1 plus dy by dx the whole square. If your curve is like from this to this, okay? If your infinitely small segments is along x-axis, what if it's along y-axis? X is a function of y, so then use the bounds as y values, right? And it should be dx. Oh, one more important thing, dy by dx, here it's dx by dy, right? And that's simple. And you can even remember in this way. Now, distance traveled by a particle. If a particle moves along a path defined parametrically by x of t and y of t, for t is t1, t2, the distance traveled is integral t1 to t2 dx by dt the whole square plus dy by dt the whole square. So it's not just x and y every time. Sometimes we use another parameter. So in that case, the distance traveled by the particle is this formula. Okay, quick example. Find the arc length of the curve y equal to x square from x is 0 to 2. Write the arc length, determine dy by dx, because in that formula you need this. And it's very simple, 2x. Now, set up the integral, the formula we know, and plug in the values, the bounds are clearly given, and compute the integral. Okay, in this case, we need to use u substitution because of the square root, right? So u substitution, and my u is 1 plus 4x square. When you differentiate it, dy is 8x dx. And let's plug in. When x is 0, and make sure you're changing the bounds also. When x is 0, u is 1. Just plugging in here. When x is 2, y will be 17. So L is 1 to 17, root y by 8 du. Okay. And root u by 8 du is what we have. Okay, so let's do one thing. Actually, here there is a change. So 1, 4x square dx square. It's 8x dx. But we didn't have an x over here. Okay, let it be 8x. Okay. So here there is a change, but if it's an 8x, this is how it will follow. Right? Okay, so we need to determine this and differentiate this stuff. And root u by 8, and you just plug in these values and simplify. This is your option for it. Right? And now, a particle moves along a path defined by x of t is t square and y of t is t cube for t is 0 to find the total distance traveled. Compute the derivatives that we need and apply the distance formula, plug in and check. Set up the integral and compute for it. So t into 4 plus 9t square dt. We can use u substitution and du is 18t dt, and also work on the bounds. 1 by 18, I just multiplied it and change this. It's root ud when you just apply these changes over here. And then you apply the power rule and solve for it. U cube by 2 by 2, 4 to 40. And just simplify this, right? This is what we got. Now, key takeaways. The main important of applications is like average value is what we did. It's 1 by b minus a, right? That kind of formula, and integrating it from a to b f of x dx. And position velocity and acceleration, how we connected position velocity acceleration from back to this, acceleration to this. And area is accumulation, like area between the curves. We see many points, like under a curve, between two curves, many intersection. And volume is accumulation of area function. We learned many methods. And arc length and distance traveled also, right? Right. So this is all about application of integration. Our next topic is differential equations. So from areas to volumes, integration brings dimensions to life, right? 2D to 3D. Yes, it can help us in every possible way. So I hope this video might be helpful, and we come to the wrap of this video here. I will be coming up with another interesting video for you. Until then, keep learning, keep practicing, keep integrating. Thank you for watching.